Is that presenting okay?
Yes.
Good.
Yes.
Good. So what we're going to do in the second part of this lecture is go through the Carnot cycle. And this is one of the first thermal cycles. So what we're going to be talking about is a power station like this, where we basically have got water that's going to go through a closed circuit. We're going to do potentially work in that water or steam. We're going to extract work out. We're also going to heat it up, so apply heat into the system. And what we're trying to do is understand the overall efficiency, where we take energy stored in fuel, turn it to heat, turn to kinetic energy, and potentially do another transformation to get electrical energy out of the system. So to find the efficiency, we need to consider energy cycles. And one of the first people to actually do this was the Frenchman Carnot. So if we look at an idealized heat system here, we need to break it down into where we put the heat into the system. So we're going to have the water expand when it becomes steam. That starts to move, so we can take kinetic energy, take the kinetic energy out from a turbine. So the work done in the turbine is going to be WT here. Then if we have the steam flowing around the system, we want to condense it back down to have water. We'll recover some heat Q2 in that particular process. And we may have to pump the water around the system, so we can use a compressor to actually pump that water around the system, increase the pressure, so it will actually flow and go through the boiler again, where we're putting a certain amount of heat in Q1. So the work we're going to do with a compressor is WCOM. And what we want to work out is the efficiency of this whole system. So I'm going to use the Greek symbol eta for efficiency in the course. And the efficiency is defined as the net work output divided by the heat input. So in this case, the net work output is the work done that we get out of the turbine minus the work that we're doing going into the compressor. So WT minus WCOM. And the heat input is just Q1. So you can see the efficiency is just determined by the heat you put into the system. Now we know that this heat recovered Q2, in this case, it could just be thrown away. So the efficiency of this system doesn't include Q2 at all. So you can consider this to be a loss in the system. Now in real power stations, what they typically do is take this Q2 and feed it back in. But in the idealized Carnot cycle, we're only looking at Q1 in terms of efficiency and the heat input. Now, if we look at the first law of thermodynamics, that was dQ minus dW equals 0. Well, for this cycle, what we've got is, well, dQ is going to be Q1 minus Q2. For dW, that's going to be WT minus WCOM, and that equals 0. But what this does allow us to do is up here, we can move WT minus WCOM onto the other side of the equation, so that WT minus WCOM equals Q1 minus Q2. And so we can substitute up here to have Q1 minus Q2. So now we can change the efficiency as the heat input minus the heat output divided by Q1. So you can see, just using the first law of thermodynamics, now we can look at the efficiency as the heat input minus the heat output divided by the heat input. Or we can rearrange a little bit that the efficiency is 1 minus Q2 over Q1. So you can see here that provided Q2 is smaller than Q1, this value always has to be less than 1. And in real systems, that's always going to be the case. Now, what we want to do is go through a derivation that we can change Q into temperature. So temperature is very easy to measure. Heat in a system actually is a very difficult measurement to do accurately, because by putting a thermometer or any other probe to measure the heat, you basically have thermal conductivity and you lose heat out the system and perturb the measurement you're trying to do. So we're going to start using the first law of thermodynamics, but our dq equals dw, we're going to put in the internal energy, du plus p dv. And of course, with the derivations we've done earlier in the lecture, with specific heat capacity and with also the Boyle's law, we can also write this as the specific heat capacity at constant volume, the incremental change in temperature plus pressure, and the incremental change in volume. So what we want to do first is look at the isotherm along AB. So an isotherm, if we look at it on the temperature versus volume diagram, there is no change in temperature, hence isotherm just means constant temperature. So dt equals 0, we can set dt equals 0 in here. That also means that the internal change in energy equals 0. So we can just write, after dt equals 0 in here, dq is p dv. So along this isotherm, we have dq equals p dv. Now, what we want to do is integrate this up between A and B. So to get the amount of heat going in, that Q1 is going to be the integral. So the volume at VB, volume at VA, and the integral pressure by dV. Now, what we can do here is use Boyle's law and PV equals nRT. So we can exchange pressure, and pressure is going to be nRT divided by the volume V. So we can rewrite this as nR, and in fact it's T1 that we've got because everything's at T1. Now dV over V, when we do the integral of this, it's just the natural logarithm of the volume V. And we're going to have V log VB minus log VA. Well, that can just be written as log VB over VA. So we get this equation that Q1 equals nRT1, the log of the volume at B minus the volume at A. Now we can do the same for Q2 going along C to D. And we end up through the same process. We get Q2 equals nRT2 because it's T2 down here, and the log of VC minus VD. So if we look at Q2 over Q1, which is what we had in our efficiency equation on the previous slide, if we divide Q2 here by Q1, we end up with this equation. So you can see at least we've got T2 over T1, but we've also got the logarithm of different volumes in the system. And what we're going to do in the next slide is actually look at how these volume parameters relate to each other, so we can rewrite this Q2 over Q1 just as difference in temperatures and get the efficiency equation to be just temperatures. So we're going to start yet again with the first law of thermodynamics, but this time we're going to look at the reversible adiabatics. So to start with, we're going to look at dA. And in this case, because it's adiabatic, we know that there's no change in heat in the system. There's certainly no input of heat. So dq equals 0. So in fact, we can have a 0 at the start of this. And so we can rearrange to have, if we move p dv onto the other side of this equation, because dq is 0, we end up with the specific heat capacity at constant volume times the incremental change in temperature equals minus the pressure times the incremental change in volume. And we're going to do the same trick that we use Boyle's law and PV equals nRT. And we want to exchange in P. So we're going to have nRT over the volume going in here. But what that also allows us to do is take the temperature from this side and move it underneath. So we end up with specific heat capacity at constant volume, dt by T, or sorry, dt divided by T equals minus nR dV by V. We want to integrate both sides. So here we've got a change in temperature between T1 and T2. And we've got a change in volume between D and A. So we want to integrate along dA, and we're going to end up getting the log and T1 over T2 equal minus NR log VA over VD. Similarly, we can do an identical process over B and C. We're going to get an identical equation, but with VB over VC. So you can now see why we've used T1 and T2 so that we can get these coming out in our system. And when we do this, we solve for it. Basically, we've got CV log T1 over T2 equals the same on this side. So we can equate these two parts. The minus nRT cancels out. We've got log VB over VC equals log VA over VD. So if we take an exponential on both sides, we end up with VA over VD equals VB over VC. So what that allows us to do, if we go back to equation 1 in the previous slide and substitute in, is that we end up with Q2 over Q1 equals T2 over T1. So this is what Carnot first did. And a key part of this to note is the adiabatic part, particularly along these two sides. So Carnot set the internal energy in the system here to be 0. And when we come to the phase diagram later on and the steam diagram, that's going to be key. So what have we ended up with? Well, this is what we left. And we've now shown that Q2 over Q1 equals T2 over T1 in the Carnot cycle. Now, in fact, Carnot originally showed it just for his steam engine. It actually works, it works in the Carnot cycle. So the Carnot efficiency of a steam engine is given as 1 minus T2 over T1. And since T2 is always smaller than T1 in any system, we basically have something that's always less than 100%. And this equates with what Kelvin later derived as the second law of thermodynamics. So Kelvin's statement of the second law of thermodynamics is that no system operating in closed cycle can convert all the heat absorbed from a heat reservoir into the same amount of work done. So what this effectively says is you cannot run any closed cycle thermal system at 100% efficiency. The efficiency is always less than 100% because there's always losses in the system. So let's see what this means in terms of efficiencies you can get in heat cycles. So Carnot is basically the maximum efficiency you can get out of any delta T in the system. We can rewrite it, and you may see Carnot written as T cold divided by T hot. That's sometimes easier for students to understand which temperature to put in and which part of the equation. And what I've done here is I've taken the cold side temperature as 293 Kelvin or 20 degrees C. And for this equation, we really want to have this done in Kelvin. And what we've got up the top is the delta T H that we have going on. So you can see if we pick 700 degrees C, what we end up with is about 70% efficiency for a thermal power station as the maximum possible efficiency. So what's beautiful about what Carnot did in the efficiency here is we only need to get the temperature to understand the maximum possible efficiency of any thermal conversion process or power plant. And you can see that 70% is probably the highest you can go. Now we'll go on later and we'll actually show some real efficiencies in the next lectures when we talk about thermal power plants and some of the renewables as well. And you'll see that, in fact, many of the thermal power plants don't get anywhere near 70% efficiency. So they're nowhere near the maximum possible efficiency. And part of this lecture, we're going to explain why that's the case a little bit later on. So the second law of thermodynamics. So both Kelvin and Clausius actually came up with the second law of thermodynamics around the same time in the 19th century. And we've already stated the Kelvin statement that no system operating in closed cycle can convert all the heat absorbed from a heat reservoir into the same amount of work. So the efficiency is always less than 100%. Around the same time, Clausius had gone through and done a different derivation where he stated that no process is possible whose sole result is the transfer of heat from a colder to a hotter body. So in effect, what the Clausius statement is saying is heat always flows from a hot to a cold body. Now, in fact, Kelvin later showed that in fact both statements thermodynamically are saying the same, or thermodynamically are identical, but they're basically saying the same thing using different parameters and different thermodynamic parameters that you can convert between each other. Now, the other thing that the Clausius statement tells us is heat can only be pumped from a cold to a hot body if we undertake work. So if we undertake work in a system, it means the efficiency is going to be less than 100%. Sorry about that. So just to show a little bit more in detail, what you'll see if you look at heat pumps, and we'll talk about...
Hi, you've reached Deb and Amy. We're not here to take your call. If you'd like...
Sorry about that. So when you look at heat pumps and you look at refrigeration, what you actually find is what's known as a coefficient of performance. And that's not actually the efficiency, certainly when you look at heat pumps and the coefficient of performance of heat pumps. So we'll just derive those because we need to use them when we talk about ground source heat pumps and a number of other renewable and sustainable forms of energy. So a typical refrigerator, what you're actually doing in the refrigerator that keeps your food cold at home is that the inside of the refrigerator basically is a cold reservoir. And you have a heat pump and you're pumping heat of an amount Q1 out of this thermally insulated refrigerator. So that heat gets taken away and set to a hot, or it's dumped into a hot reservoir at temperature T2. Now we need to do some work done. So we need to put energy W into the heat pump to actually pump the heat away. And the heats that we're going to dump into the hot reservoir T2 is going to be the heat that we take out of the cold reservoir plus an amount for the energy input, the work done on the heat pump, so that the heat going into the hot reservoir T2 is the heat coming out of the cold reservoir plus the work done on the heat pump. Now, for refrigerators, we're interested in the temperature at the cold end. And so the coefficient of performance of a refrigerator, so coefficient of performance for a refrigerator is Q1 divided by the work done W. Now, we can basically use first law of thermodynamics and dQ equals dW. So dQ is just Q2 minus Q1. And so we end up with Q1 over Q2 minus Q1. We know from the Carnot cycle, of course, and we just proved that Q2 over Q1 equals T2 over T1. We can put that in. And so the coefficient of performance of a refrigerator can be rewritten as T1 over T2 minus T1. Or you can also divide out in this, but that's the coefficient of performance of a refrigerator. Now, what we're going to be much more interested in terms of ground source heat pumps for renewable and sustainable heating of properties in later lectures is a heat pump system. So in this case, the ground is probably the cold reservoir, and we want to pump heat out of the cold reservoir. Now, the Clausius statement stated that heat is always going to flow naturally from the hot reservoir to the cold reservoir. But it still allows that we can add energy or work done to take heat and move it from a cold to a hot reservoir. So the point about the Clausius statement is that if there is no work done, heat will flow from the hot reservoir to the cold reservoir. But if we do work done with a heat pump, then because we're putting energy in and the efficiency will go down, or while it's costing us energy to do that, we can transfer heat from a cold to a hotter body. But when we look at the coefficient of performance, because this time it's the hot end we're interested in, the coefficient of performance for a heat pump is defined as the heat going into the hot reservoir divided by the work done. So if you compare this with refrigeration, you can see how it's the interest of the hot end is the heat that we're actually putting into the coefficient of performance. Now we can do the same tricks as we did before. First law of thermodynamics and dq equals dw. So w can equals q2 minus q1. And we change it around. And this time, rather than like the refrigerator, T1 over T2 minus T1, it's T2, so the hot reservoir divided by T2 minus T1. So the reason I've got interest in the cold end and interest in the hot end is when you look at the coefficients of performance, you can see that for the refrigerator, we're interested in T1 in the cold end. So that's the numerator in the coefficient of performance. For the heat pump, we're interested in the hot reservoir and the temperature at this end. And in the coefficient of performance is T2 over T1. We can also write this as 1 plus the coefficient of performance for a refrigerator. Now, some students always get a bit confused when they first see coefficients of performance for heat pumps. And you'll see in the next slide why. Because the coefficient of performance of a heat pump is always greater than 1. It's not the efficiency. So a key thing to realize is the coefficient of performance of a heat pump is not the thermodynamic efficiency. So hence, this is not a perpetual motion machine. It's not a machine that's generating energy from nowhere. This is a figure that bears nothing to do with thermodynamic efficiency. So, of course, we've derived the Carnot version of this where it's completely perfect and the coefficient of performance, it's the maximum value you can get. So the maximum value is T2 over T2 minus T1. In real heat pumps, there's always going to be more losses in the system that are not accounted for in this ideal system using the Carnot efficiency to derive the maximum possible efficiency. So in real heat pumps, the coefficient of performance is always less than T2 over T2 minus T1. Okay, so that's where we're going to take another break. Has anybody got, well, what I'll do is I will stop the recording.